Physics students. Today we're going to be talking about Chapter 2, Section 3, which is really about acceleration. Now you remember from your basic physics that acceleration is a rate of change. It's a change in velocity, which is a vector, over a change in time. So when we think about acceleration, we can think of it in terms of average acceleration being a change in velocity over change in time. This should probably be directional specific, so if you have an x here, you should have an x here. Y or z, the frame of reference matters. But the main idea here with understanding acceleration is that average acceleration, again, if you're making a graph of velocity versus time, what we see is that if you have a curve on a velocity time graph, that certainly indicates that you have a changing velocity over time. If you just find any 2 points on that graph and find the slope of the line between those 2 points, you're looking at the average velocity. You're looking at the difference between the starting velocity and the final velocity, which is your change in velocity, and the difference between your starting time and your ending time, which is your change in time. And then you can use the equation to figure out the average acceleration. Keep in mind that accelerations go with forces, so if you're dealing with an average acceleration, that means that you have a force, a push or a pull in the direction you've indicated, in this case, x. So a push and a pull to the left or to the right. Positive accelerations mean the object is being pushed or pulled to the right. Negative accelerations do not mean slowing down. It means that the object, the particle, is being pushed or pulled to the left. Let's take a look at an example of average acceleration. This is in your book, example 2.2. This is located on page 44. An astronaut has left an orbiting spacecraft to test a new personal maneuvering unit. As she moves along a straight line, her partner on the spacecraft measures her velocity every 2 seconds, starting at time 1 second after she started floating out there. And so we have a data table here, and what we can see is that her velocity as she moves along is changing in a very kind of erratic way. We can see that her velocity starts at 0.8 meters per second at the instantaneous time t equals 1. And then we see that it increases to 1.2 meters per second. And then it increases to 1.6 meters per second. So during this time interval, these first 3 time data points, we see that it's increasing by 0.4 meters per second. So it's increasing in kind of a constant way. Then it decreases, and then we see that her instantaneous velocity actually changes direction here and changes in magnitude as well. So if we wanted to figure out the average acceleration, the graph that we see here kind of shows those accelerations on a velocity time graph. We see that the slope of a velocity time graph tells us acceleration. And so we can see that here we have a positive slope. Here we have a negative slope. Here we see that the quadrant that we're in, these are all positive numbers, and down here, this is quadrant 1, that is positive. Quadrant 4, all these numbers are negative. So the key thing for thinking about speeding up and slowing down is here we can see the average acceleration is positive and the velocity is positive. So a positive and a positive means speeding up. Here we can see the slope is negative, but it's in the positive quadrant, so a positive and negative means slowing down. Here we can see in this next interval the slope is negative, but it's over here in the negative quadrant. So the slope is negative, but it's moving in the negative direction, so it's actually speeding up right here. And here we can see that the slope is positive, but it's in the negative quadrant. So with a positive slope and a negative quadrant, we see that it's actually slowing down. Or you can see, project this, it's getting closer and closer to 0. means slowing down. So reading these graphs and making these graphs is something that I think you should spend some time with. But recognize that because you're dealing with only 2 points, you're dealing with average acceleration. I highly recommend that you take a look at the FET that's at this link, and you'll see, in particular, this one has to do with forces. And because it has to do with forces, you see that there's a place here for you to graph acceleration. And because you're graphing acceleration, graphing velocity, graphing position, you have some buttons that allow you to really take a look at this and connect the idea to forces. Let's talk a little bit about instantaneous acceleration. Remember, an average is the slope between 2 points. But it's pretty obvious that back here, that although the slope between these 2 points is the average acceleration, that there are other points along the way where the acceleration is the slope of the curve, tangent to the curve at different points. Here you can see that the slope of the tangent to the curve at different points is not necessarily the same slope in magnitude as the average. That's because the instantaneous acceleration is changing, even though the average between those 2 points is not. Well, when we talk about that, what we're really talking about, again, is the idea of a limit. And in AP Physics, a limit describes as the time interval at which you're looking at this change in velocity. As the velocity changes with time interval, this time interval right here is really a long time interval when you think about the graph that we were just looking at. All right, we can see that this time interval is over a very long period of time. It's such a significant amount of time that T1 and T2 are 2 very discrete points, very distinct points. But what if those points were so close in time that it was an instant in time that was almost discernible, that you could almost not see that there were actually a starting time and an ending time, but it seems like just one instant in time? Well, that would lead us to understand instantaneous acceleration, which I think I mentioned in a previous video. This triangle means delta, which means a change in, but it's a capital D, capital delta, the Greek letter delta. And because it's a capital letter, it means a big change in velocity over a big change in time, which is exactly what we're seeing here. A very big change in velocity and a very big change in time. And so we use deltas for the change. But as that change in time gets closer and closer and closer to 0, as that time interval gets smaller and smaller and smaller and smaller, so that there doesn't seem to be a very big delta t, but instead a very, very, very small delta t, we use derivatives, and we use actually a lowercase d, which is also the letter delta, but it's a small delta, a lowercase delta, indicating not really, really, really big changes in time and really, really big changes in velocity, but instead it means really, really teeny-weeny, little small changes in velocity over teeny little changes in time. So we take this idea of a limit and we use it to describe a derivative. And ultimately, where we go with that is this statement right here, that acceleration, instantaneous acceleration, is the change in velocity, teeny little changes in velocity over teeny little changes of time. And then this notation, for those of you who are kind of new to calculus, indicates that, don't forget, velocity itself is a change in position over time. So what we're really saying is teeny little changes in teeny little changes in position over time. And we call this a second derivative. Here you can see the notation. The second derivative of position and time is acceleration. So here we can see acceleration is the first derivative of velocity, and it's the second derivative of position. Again, when you're calculating a derivative, a good way to think about this is to say, well, if I had a position time function, and I'm just making one up here off the top of my head, all right, I just made up this function. If I had a function that describes an object's position, then its velocity can be calculated by using some basic calculus, and that is, its velocity is going to be the derivative of its position over time. And the way we do that, again, is we take the exponent, we multiply it by the coefficient in front, so it's going to be 10t, and then we subtract 1 from whatever the exponent was. So 2 minus 1 is 10t to the first. This is actually t to the first, 3t to the first. So 1 times 3 is going to be 3t to the 0. And this is actually 2t to the 0. So 0 times 2 is 0. Ultimately leaving us with 10t plus 3. So what you find is that our position time function is probably a parabola. This looks like kind of a parabola. And when we do the derivative, we get a line. What if we wanted to go on and indicate the acceleration time function? Well, this would just be the derivative of the velocity time function. So again, this is 10t to the first, so this is going to be 1 times 10 is 10, t to the 0. And this was 3t to the 0, so this is going to be plus 0. Or in other words, our acceleration is just going to be 10t. This is a pretty classic way of going through and moving from position time to velocity time to acceleration time. And here you can see that velocity is the first derivative of position, and then this is why we say acceleration is the second derivative, because you had to do an additional derivative to do it. I do want to mention a little bit about position time graphs and velocity time graphs. Then again, the key thing to pay attention, these graphics show, is to pay close attention to the slope. With position time graphs, when we look at the slope, we recognize that the slope of position time graphs gives us velocity, and the slope of the velocity time graphs gives us position. Keep in mind that describing that particle then is kind of described with these things called motion graphs here, and you can see that as you look at this velocity time graph, we see that we have a positive slope in a negative quadrant, which means it's slowing down. And here you can see the velocity and the acceleration have different directions. The object is slowing down. I know it's slowing down because here's 0, and eventually it crosses that line. If it touches or crosses that line, the object stops. And so we can see that the object is going to actually come to a stop. And then here we can see that it crosses into the positive quadrant, but it has no slope. No slope on a velocity time graph means no acceleration, so it's actually moving at a constant velocity for some period of time. Here we can see that the slope is negative in a positive quadrant, so it's slowing down again. And right here is a point where it stops. And then eventually it has a negative slope in a negative quadrant, so that makes it speeding up. Here you can see the acceleration and velocity of the same direction that object's going to speed up. So another good example you could look at is example 2.3 in your book. It says the average and instantaneous velocity can be viewed again from this point of view of a function. So imagine you had a velocity time function given here, that the velocity is 60 meters per second plus 0.50 meters per second cubed t squared. So this describes how velocity is changing with time. If you wanted to figure out the change in the velocity during a certain time interval and then find its acceleration, one really, really good way to do this might be to take the derivative here. If you take the derivative, though, remember it'll give you the instantaneous velocity, or excuse me, instantaneous acceleration, and then you would need to plug in the numbers into that function to find